Good morning. So first I will set the scene and then focus on the Rosetta mission and then its target 67P theorem of Gerasimenko or Cherry. And then I will speak about our involvement in the Department of Physics in this mission, and then speak about what is coming next for the mission. A comet has a nucleus which is made of frozen volatile, mainly H2, but also CO, CO2, ammonia, and organic materials, and also dust grain. Typically comets are a few kilometers to a few tens of kilometers, and when they get close to the sun, then you have the formation of a dust tail and a plasma tail, which actually led to the discovery of the solar wind and is a very good probe of the solar wind, for instance, to derive its speed. Comets are made of material which was used then to create the solar system 4.6 billion years ago. And the advantage, unlike planets, is that they are in reservoir beyond the orbit of Neptune, so they are nearly pristine material. They have not evolved until they are kicked in to the solar system. They may have also brought water and seed of life at Earth, and so they are very interesting bodies and crucial bodies to learn about. Since 1985, there have been space missions visiting comets. In '96, there are many which visited Halley, and in particular Giotto, which is the first interplanetary European Space Agency mission, which provided the first image of a nucleus of a comet and reached a distance less than 600 kilometers from the comet. I would like to highlight also Deep Impact, which sent an impactor on Temple 1, and then Temple 1 was visited a few years later by NEXT. And finally Stardust, which took a sample of the coma, and then the sample return capsule was brought back to Earth in January 2006. But the closest distance from the comet was 181 kilometers. Just one highlight here is, for instance, at Halley 2, observed by epoxy in different emission and absorption feature, and you can see that it's very complex. The outflow gas varies in terms not only of location but also on composition here of CO2 on the sunlit side, while the H2 vapor come from another part. However, so all those missions have increased our understanding and learning of knowledge of comets, but all of those were actually a snapshot, and so at a given distance from the sun. So what is bringing Rosetta? Rosetta is the first comet to rendezvous with, first mission to rendezvous with a comet, to orbit around the cometary nucleus. We saw earlier, put aside the impactor, the closest distance was 181 kilometers. Here, Rosetta will go below 10 kilometers. To escort a comet instead of just having a snapshot at a given heliocentric distance. Here it will basically walk with the comet because it will have a relative speed to the comet of 1 meter per second. So really walk with the comet from 3.6 AU, 1 AU is the mean Sun-Earth distance, about 150 million kilometers, down to perihelion at 1.3 AU. And then which will release a lander Philae on the comet at 3 AU in November, and the lander will then make the first in situ measurements, not only on the surface but actually subsurface below 20 centimeters below the surface. Rosetta is also a first flying beyond 2 AU up to actually beyond 5 AU using only a solar panel using an innovative solar cell technology. So that's definitely one of the most complex and ambitious missions ever undertaken. What are the aims of Rosetta? So it's to provide clues to decode the composition of the early solar system, as the Rosetta Stone was used to decode the Egyptian hieroglyph. It will provide clues to help understand the evolution of the solar system by the measurements of isotopic ratios, and be able to, the next, Next, here's glycine, which was detected in the sample returned by stardust. So glycine is the most basic amino acid and a precursor to a protein. And at the onboard Rosetta, there is the ionized and mass spectrometer, which can actually analyze up to 1,800 EMU. Glycine is 75. And also, because it's escorting the comet, as the comet gets closer to the sun and develop its coma, it will be able to study the development of the cometary activity. So Rosetta was launched in March 2004, 10 years ago, and after a long tour, so to reach large distances from the sun, the black line represents its trajectory. It needed gravity assist, which did by a flyby of Mars, whose orbit is shown here in red, and 3 flybys of the Earth, whose orbit here is shown in green. And then it also flew by two asteroids, included Rhodesia, provided those amazing pictures of the surface, went on and then went on with hibernation from June 2011 up to January 14 this year, and then a rendezvous successfully with the comet on August 6 this year, with the landing planned on November 11, and then we'll continue to follow the comet. In blue you have the cometary orbit. Follow the comet to perihelion, and then up to the end of mission, which is planned in December next year. So what are the instruments on board Rosetta? So they are different dust analyzer, which will estimate the momentum, composition, size. There will also the analysis of the gas with mirror and with Rosina, and mentioned isotopic ratio. It has actually a mass resolution, one of the sensors on Rosina, over 3,000. There is also a UV visible and infrared spectrum, visible cameras, and the Rosetta Plasma Consortium, which has 5 sensors. I will come back on those later on. And there is also the communication antenna, which is used to do a radio science, and the Consortium, which is an instrument which has sensor both on the orbiter and on the lander to probe the nucleus, the interior of the nucleus. And there is Philae here, which is as big as a wash machine, 100 kilos, and which has 20 kilo of actually payload, included cameras, plasma and magnetic field measurements, and electric properties will be measured. There is also a driller system, which then will take a sample below the surface, heat it in the oven, and then you have different instruments such as Ptolemy, Kozak, and SIVA, which then will analyze the release gas. Okay, but what is the target of Rosetta? That's 67P of Gerasimenko, which is a Jupiter family comet. Jupiter affected its orbit and reduced its perihelion from 4 to 3, and ultimately 1.3 AU in 1959, which then led to its discovery in September 1969 by Klim Churyumov and Svetlana Gerasimenko, which are 2 Ukrainian astronomers. It's a relatively modest activity. I mean, compared with Halley, for instance. However, it's still quite significantly outgassing. Speak about the engineer who has to fly this big spacecraft. I mean, I spoke about the solar panel earlier. The spanning is 32 meters, so it's longer than a basketball court field. And the rotation period is over 12 hours, and the orbit period around the Sun is over 6 years. Here was the knowledge of the model of the comet before the arrival, arrival of Rosetta, based on observation from the Hubble Space Telescope. Well, and here is observation taken by Rosetta on July 14 last year. So you can see that it has a quite complex shape. It's a bilocate shape with a large, it has been referred as a space duck. And with the head here and with the body here. So for reference, I will refer to that later on. There has been observation, for instance, with Vertis, temperature observation of the surface, which show that the temperature is higher than predicted, so showing, attesting of the surface covered by dust. And here's an amazing picture taken by the Osiris camera, which shows a very complex surface with some people would think craters. It may be rather more depression in the terrain, and you have a steep cliff, 300-meter, and you have layering, and more smooth in the neck here with some boulders. And as for the sizes, so the larger here, it's 4.1 kilometer for the body of the, and the first estimate for the density is 0.4 gram per cubic centimeter, so very porous. So the rendezvous was successful on August 6, 2004. But Rosetta didn't go into orbit right away. It went through actually a very complex maneuver because it wanted to estimate the gravity of the comet and the outgassing as well. It arrived on the day side. Actually, it slowed down. If the sun is behind me, then the comet was there, and Rosetta slowed down through burst burning to catch up on the comet and arrive on the day side, because as you have seen, it's relatively great. It's a low albedo. So it had to arrive on the day side to be able to see it. And then finally went into orbit in September. Another picture here which shows that the neck of the duck is quite outgassing, and the Rosina instrument have shown that there is a strong diurnal variation. The total number density change also in composition. So very interesting observation. And here another with Cosima, where the split of 1 centimeter by 1 centimeter was exposed for 2 weeks in August, and then you have the detection of a dust grain. You have an LED here on the right, and then from the shadow you can estimate the size, which has the same size as the human hair. And then now they are going to look into composition. Okay, what is our involvement in the mission in the Department of Physics at Imperial College? So we are strongly involved in the Rosetta Plasma Consortium, which is made of 5 sensors: the Langmuir probe, which measures the thermal, electron, and ion density and temperature and ion velocity; the magnetometer, which measures the 3 components of the magnetic field; the mutual impedance probe, which measures at high accuracy the absolute electron density of the thermal plasma and electron temperature; the ion composition analyzer and ion and electron spectrometer, which measures the suprothermal electron and ion population and ion composition. And we have built at Imperial College the plasma interface unit, which controls and powers all those sensors. I'm very grateful to all the RPC PI which have allowed me to show you those data, which were taken on August 29. And which shows as a function of time on that day from 012 to 24 UT at a distance as close as 30 kilometers. The data from the Langmuir probe, the ion and electron spectrometer, ion composition analyzer, the amplitude and the phase from the mutual impedance probe, and the 3 components of the magnetic field. I'm not going to go over all details. All the data. I just would like to highlight this anti-correlation between those 2 strips here, which represent the solar wind. Here it's energy, the solar wind proton and highly ionized helium, and the suprathermal electron population and the signal received by a MIP. So you have a clear anti-correlation. And this plasma here is definitely not solar wind. You have here a signal around 10 kilohertz, which correspond to the plasma frequency and correspond to about a density for the thermal electron population of 100 per cubic centimeter, which is about 2 orders of magnitude higher than the solar wind. And so that was not expected, this anti-correlation, and we are working on the interpretation. So I've mentioned that the plasma package interface have been built at Imperial College. The PI for operation for RPC is Chris Carr, the RPC operation manager Emmanuel Cupido. So we have a strong operation, but also archiving activity in the group. All the data will be archived at Imperial College, and Tony Allen is coordinating this effort. Of course, we are also interested in the science, and not only in the data analysis. We have also developed a model which ultimately will be used as organizing element of multi-instrumental observation of the RPC and other instruments like the Rosina instrument. And we're interested in solar wind coma interaction and cometary plasma. And two research associates, Lorenzo and Martinini and Susala Raghuram, have a poster if you would like to learn more about it. I would like to highlight only one thing. It's one modeling result that we had done with my previous research associate, Eric Vigren, who now joined the RPC long-range probe in Sweden, and we're continuing this activity. That's here what is shown, that simulation, and it's the comet-centric distance as a function of the number density of the electron and the ion. In pink, that's the result of the electron and ion density from the comet in a pure gas phase, so we neglect the influence of dust. And then all the other curve is when for a simulation, a result for a simulation when dust is included. So when we include dust of 200 nanometer, then the dust particle become highly charged. However, the electron and ion density, ion in the gas phase, are not strongly affected. However, if you include 2 nanometer grain, then they will electron will attach to the grain, not because they are very small, only one charge will be efficient. So here is the profile of the dust grain which are charged -1. Here are the density of the dust grain which are charged -1, and you can see that there is a strong depletion in the electron density, so the nanograin have a strong effect. Overall, we will study with RPC the activity of the comet as it gets closer to the sun, the interaction with the solar wind, and the inner structure of the cometary coma, among others. So what next? Well, 10 days ago, the ESA selected the Philae landing site. So the landing site has been the primary landing site has been chosen in the head of the space dock, and the criteria included the solar illumination, communication, accessibility when Rosetta will release the lander, because the lander has no capability of changing its trajectory. So it's passive mode once it's released, and steepness of the slope, because you want the lander arrive not upside down, and we want that so the slope shouldn't be larger than 30 degrees. And some activity, because not too much, but some activity to make it scientifically interesting. And so the release is of Philae from Rosetta is expected on November 11, when the comet will be at 3 million kilometers from the sun, so 450 million kilometers from the 3 AU, 450 kilometers from the sun. And so it will be released, and then during the descent, measurements will be taken. The philae will sniff the atmosphere, for instance, and that will take from 5 to 10 hours. And then philae will be landing with a first battery, which will last 54 hours. That's the minimum nominal mission. But it has, during this time, it will actually orient its solar panel to make it optimum for then recharging those batteries, and it could last up to March 2015. The key thing will be the landing, because the gravity on the comet is extremely small. And so there is different technique. There will be the harpoons, for instance, screws, and also a burst to try to keep the probe down. Because even if it's 100 kilo on such a low gravity body, it will be important to try not to bounce. All the instrument on board, not only the Rosetta instrument, but on philae seems to work. And here is a picture taken by the camera on philae on the lander of the solar panel with the comet on the background. So Rosetta is a unique cometary mission with an orbiter and a lander, an escort phase, and it has been already scientifically and technologically very successful. It's currently flying actually at 55,000 kilometers per hour at 30 kilometers from a comet. Yesterday there was the first night excursion, and only one actually. Then in September 29th, it will go in closer to 20 kilometers. Then October 10 to 10 kilometers, and finally the landing expected on November 11. The water snow line should be crossed in January 2015, with perihelion reach at 13 on 13 August 2015, and the strongest outgassing rate should happen a little bit actually after that, with the end of the nominal mission in December 2015. And if you're interested to keep up on the latest on Rosetta, I strongly encourage you to check the ESA website, the blog website, and there is also a UK website. Thank you very much for your attention.